It's single speed from 0 to 200 miles an hour. The RPM is so crazy that just the centrifugal force wants to expand the rotor.
Something historic just happened in the electric vehicle industry, and Elon Musk's excitement says it all. Tesla has officially built its most powerful engine, and it has left rival companies in absolute disbelief. We are not talking about a minor upgrade. It's a breakthrough that allows a heavy sedan to rocket from 0 to 60 in under 2 seconds, while simultaneously delivering a massive 400 miles of range. Global giants like Ford, General Motors, and Volkswagen, who have spent over $500 billion trying to catch up, are completely silent, because what Tesla just built might make their entire future obsolete. But what exactly is this mechanical miracle, and why are competitors struggling to answer it? Let's dive in. The impossible motor. Inside every electric motor, there is a core part that decides everything: power, speed, and efficiency. It is called the rotor, a spinning cylinder packed with copper windings and electromagnets rotating inside a tight space. Now, here is the problem no one could fully escape. As the rotor spins faster, it starts fighting physics itself. At extreme speeds, the outer edge of the rotor can experience forces reaching several thousand times the force of gravity. The copper inside is heavy, and under that pressure, it does not stay fixed. Because of centrifugal force, it begins to stretch outward, almost like it is trying to tear itself apart. Even a movement smaller than a fraction of a millimeter becomes dangerous because the gap between the spinning rotor and the outer stator is microscopic. That air gap is designed for maximum efficiency. If the rotor expands and touches the stator, it destroys the motor instantly. For years, engineers tried to control this using high-strength steel sleeves wrapped around the rotor. Strong, yes, but heavy, and worse, when metal spins at high speed, it creates hidden energy loss inside the motor, turning useful power into wasted heat. This was the limit. Faster speed meant more risk. More risk meant bigger motors. Bigger motors meant heavier cars, a dead end that every company accepted. Then came Tesla, and it changed both the material and the entire approach. Instead of metal, they used a carbon fiber sleeve, a material widely used in aerospace, rockets, and high-pressure engineering systems. It is extremely strong in tension, incredibly light, and almost does not expand with heat compared to steel or aluminum. That small detail changes everything. Because while metal sleeves slowly loosen under heat and stress, carbon fiber stays locked in place, constantly compressing the rotor. And unlike metal, it is non-conductive and non-magnetic, meaning it does not interfere with the motor's magnetic field. It removes those hidden energy losses that quietly reduce efficiency in traditional designs. Now the rotor is held in a completely different way: stable, tight, controlled, even at extreme speeds, reaching around 20,000 revolutions per minute in performance versions. But building this is where the real difficulty begins. Carbon fiber only works when wound under extreme precise tension. Tesla had to design custom robotic machines to wrap thousands of fibers with exact pressure, because even a tiny mistake can create weak points that only appear at full speed. And at that level, something surprising happens. The motor becomes extremely compact for its output. In some configurations, a unit small enough to fit in a carry-on bag can generate over 600 horsepower, changing how much physical space a car actually needs. But when engineers and teardown experts first saw this, the reaction wasn't excitement, it was hesitation. And it wasn't just them. Even the legacy giants, like Ford, GM, Toyota, and Volkswagen, are unusually silent about this breakthrough. So before we go further into Tesla's new motor and how it's pushing its ecosystem to another level, we need to look at something more important. Why is no one responding at all? Silence of giants. What makes this moment even stranger is not just the motor itself, but what came after it. Because in a normal industrial race, this is where things explode publicly. For example, When Toyota pushed hybrid technology forward with the Prius, competitors like Honda quickly responded with their own hybrid systems like the Insight. When Ford improves truck performance, GM almost immediately answers with a rival upgrade in the same segment. That back-and-forth reaction is normal in this industry, but here, that pattern breaks. The first reason is timing. Legacy automakers like Ford, GM, Volkswagen, and Toyota operate on long product cycles of around 5 to 7 years. Once a platform is locked, it cannot be changed easily. Over the last decade, these companies invested more than $500 billion into electrification, building entire EV architectures around fixed motor designs, mostly steel-sleeved rotors, and conventional induction systems. So when Tesla introduces a carbon-wrapped high RPM motor that changes the balance of size, speed, and efficiency, it arrives at a time when their decisions are already locked in. Factories are built, supply chains are set, and production tools worth billions are already in place. They are not free to react instantly. But there is a second reason too, and this one is the main one. Inside every major automaker, there is something called competitive teardown. When a new vehicle enters the market, companies don't ignore it. They buy it directly, bring it into engineering facilities, and dismantle it completely. Every part is measured, analyzed, and compared against internal designs. This is standard practice across the industry. So Tesla's motor is not unseen. It is being studied in detail. But what happens next is where the problem begins. Because when engineers break it down, they can clearly identify the structure, the carbon fiber rotor sleeve, the ultra-high RPM design reaching around 20,000 revolutions per minute, the compact size producing over 600 horsepower in some configurations. They can see how it works. They can measure everything. But even with the most advanced factories and machines in the world, they still can't build the exact same motor. And that raises one strange question. Why? Why is Tesla's engine still impossible to copy, even when it is fully understood? The manufacturing wall. Designing a breakthrough motor is one thing. Building it at scale is something completely different. Because in engineering, a prototype is not the real battle. A prototype is made slowly by expert engineers in controlled labs where every step is adjusted by hand. It is impressive, but it is not reality. Reality begins when you try to build that same thing millions of times. At that point, even tiny flaws stop being small. A microscopic defect that appears once in 100 units becomes a major failure when you are producing thousands of motors every single day. The system cannot pause. It cannot slow down. It either works continuously or it collapses under its own error rate. And Tesla's carbon-wrapped rotor pushes that problem even further. Inside the motor, two materials are locked in conflict. Copper expands when it heats up during operation. Carbon fiber barely expands at all, so when the motor runs at high load, the copper tries to push outward, but the carbon sleeve refuses to move. This creates extreme internal pressure, reaching tens of thousands of PSI. At that level, even a slightly uneven wrap is dangerous. Because the stress does not distribute evenly, it concentrates in small points, and that is where the carbon fibers can start to shear. If that happens at high RPM, the rotor can fail instantly. So precision is not optional, it is survival. But here is the bigger issue. Standard manufacturing machines were never designed for this. Carbon winding equipment exists, but it is meant for simple structures like pipes or pressure tanks, not fast-moving, high-tension, rotating electric motor cores. So Tesla had to build its own custom robotic winding systems from scratch. These machines operate under extreme tension, pulling carbon fiber to its absolute limit while wrapping it around a spinning rotor. Even then, the process is unstable. The system uses real-time laser tracking and cooling controls to stop the fiber from snapping or misaligning during production. And this is where most companies fail. Because if your production line has even a small defect rate, like 5% scrap, the losses scale into billions. Companies like Rivian, Lucid, and others struggle here, not because they cannot design good motors, but because they cannot sustain the manufacturing pressure long enough to make them profitable. That leads to a deeper question. If Ford, General Motors, Toyota, Volkswagen, and Mercedes-Benz, the industry giants that have been in the market for decades, are struggling to replicate it, how did Tesla actually manage to do it? And the answer isn't technology, it's pressure. A kind of pressure Tesla went through that almost nobody really knows about. Pressure before breakthrough. Tesla did not build this motor when everything was going right. It built it when the pressure was starting to close in from every direction. Back in the late 2000s and 10s, Tesla had a huge advantage. If you wanted a modern, long-range electric vehicle, there were very few alternatives. In many markets, Tesla was the obvious choice, but that world did not last. Between 2019 and 2025, the EV market changed completely. Ford, Volkswagen, Hyundai, Kia, BMW, Mercedes-Benz, BYD, Rivian, Lucid. Suddenly, the market was crowded with new choices. Customers who once waited months for a Tesla could now pick from dozens of electric SUVs, sedans, and trucks. And the numbers reflected that shift. Tesla's share of the US EV market fell from roughly 75% in 2019 to below 50% as competition grew. Tesla was still the leader, but for the first time, being the only advanced EV company was no longer enough. Then came the Cybertruck. When Elon Musk first revealed it in 2019, it looked like something from a science fiction movie. Tesla presented it as proof that the company could completely rethink what a vehicle could be. But reality proved more complicated. The radical stainless steel design divided buyers. Years of delays followed. Production became far more difficult than expected. What was supposed to showcase Tesla's manufacturing strength also exposed just how hard it was to keep reinventing production at scale. At the same time, Tesla faced growing scrutiny. As millions of vehicles reached the road, regulators, journalists, and customers examined every problem more closely. Panel gaps, suspension concerns, software recalls, driver assistance investigations. Each issue created more pressure on the company. And this was happening while competitors were getting stronger every year. Most companies facing that situation would do the predictable thing: cut risk, reduce research spending, focus on protecting profits, stick with proven technology. But Tesla chose the exact opposite path. Instead of playing defense, it approved one of the most difficult motor projects the automotive industry had ever seen. A project built around new materials, new manufacturing methods, and engineering limits that many believed were too risky for mass production. Because Tesla understood something important. If it kept making small improvements to ordinary electric motors, eventually everyone else would catch up. The company did not need a small advantage. It needed a leap, something that would force the entire industry to rethink what an electric vehicle could be. Breaking the trade-off. In automotive engineering, almost every design is built on compromise. If you tune a motor for extreme acceleration, you lose efficiency. It burns more energy, creates more heat, and drains the battery faster. If you tune it for maximum efficiency and range, it becomes weaker in performance. It cannot deliver repeated high power without slowing down. That trade-off was accepted for decades because at the center of the problem is physics itself. To get more power, you push more current through copper windings, but that creates resistance losses known as I²R losses, which turn energy into heat. And as speed increases, traditional metal parts also create eddy current losses, where the metal itself fights against the magnetic field and wastes energy as heat. This is why high-performance electric cars usually cannot maintain peak acceleration. After a few hard launches, they must slow down to protect themselves from overheating. Tesla approached this differently. The key change was the carbon fiber sleeve around the rotor. Carbon fiber is non-magnetic and non-conductive. That means it does not interfere with the motor's magnetic field, and it does not generate eddy currents. So instead of wasting energy as heat, the system keeps more of it as usable motion. Even more importantly, this allowed Tesla to tighten the air gap between the rotor and stator, creating a stronger and more focused magnetic field. The result is extreme efficiency. Around 97% of electrical energy can be converted into motion instead of being lost as heat. And that changes everything, because now performance and efficiency are no longer fighting each other in the same way. This is why the Tesla Model S Plaid could hit 0 to 60 miles per hour in 1.99 seconds, powered by a tri-motor setup, while still maintaining long-distance efficiency of around 400 miles of range under EPA estimates. But the more important detail is not the number itself. It is consistency. Unlike traditional high-performance EVs, the Plaid can repeat extreme acceleration runs multiple times without dramatic thermal drop-off. It does not quickly run out of breath after a few launches. It stays stable across repeated stress. Now, after building the most powerful engine, and after stabilizing production at scale, Tesla was left with just one final battlefield: price. And what it did there almost erased the competition entirely. The cost war. In the real world, even the most advanced technology means nothing if it cannot be built at a price the market accepts. That is where the real competition begins, and Tesla started attacking that layer directly. The company's target is a complete integrated drive unit costing around $1,000. This is not just the motor. It includes the carbon-wrapped motor, inverter electronics, and single-speed gearbox, all combined into one compact system. To understand how aggressive this is, most legacy EV drive units cost around $3,000 to $5,000 to manufacture, some even more, and internal combustion engines alone often sit in the $2,500 to $4,000 range before other systems are added. So Tesla is not just lowering cost, it is compressing an entire powertrain into a price point competitors struggle to even reach with basic systems. Part of this comes from structure. Tesla avoids traditional supplier chains wherever possible. Instead of paying external companies like Bosch or Continental, which already include profit margins in their components, Tesla builds major parts in-house. That removes layers of markup and reduces dependency costs. Another factor is materials and design. Tesla has been working on reducing reliance on expensive rare earth minerals like neodymium, dysprosium, and terbium, which are widely used in traditional high-performance motors for strong, permanent magnets. This cuts supply chain exposure and lowers raw material costs. But the most important force is not a single decision. It is the compounding effect. Lower cost allows lower pricing. Lower pricing increases demand. Higher demand increases production volume. Higher volume reduces cost further, and the cycle repeats, faster each time. This is where the pressure builds on competitors, because legacy automakers are structurally locked into higher costs, supplier dependencies, and slower production systems. Competing directly at Tesla's price level often means selling EVs at a loss. So they are forced into a difficult position: either match the price and lose money, or protect margins and lose market share. And that is where the real tension starts to form. Because this is no longer just about building better electric cars. It is about whether anyone else can survive a cost structure that keeps dropping faster than they can respond. But Tesla isn't stopping even there, because what Elon Musk is building doesn't stop at engines or pricing. It goes far beyond both. He is quietly building a system so advanced that the rest of the industry is struggling to even understand it. The self-reinforcing machine. If legacy automakers are still thinking Tesla is just a car company building advanced motors and batteries, then they are looking at only a small piece of the picture. Because the carbon-wrapped motor, the cost reductions, even the vehicles themselves, are not the real product. They are just nodes in something much larger. a global system that keeps feeding itself. It starts with data. Every Tesla on the road is constantly collecting real-world driving information. Millions of cars, across highways, cities, deserts, and snow. Every strange moment on the road, a sudden cut-in, a weird pedestrian movement, unusual weather, gets recorded and sent back. This creates billions of real-world miles every year, a scale that no competitor can realistically match without the same fleet size already in motion. That data goes straight into Tesla's AI systems, and to process it, Tesla built its own supercomputer system called Dojo, a machine designed specifically to train driving intelligence using massive video datasets. Instead of taking weeks, training cycles are being pushed down dramatically, creating faster and faster improvement loops. More cars produce more data. More data improves the AI. Better AI makes the cars smarter. Smarter cars attract more buyers. And the loop keeps tightening. At the same time, Tesla controls the full stack: battery chemistry, AI chips, motor design, software, all built in-house. This allows the system to push hardware closer to its limits without breaking. Faster response, tighter control, and efficiency that fragmented competitors cannot match. Then comes infrastructure. Tesla's supercharger network, once seen as just support, has now become the industry standard. Even rivals like Ford and General Motors are adopting Tesla's charging system. So now, everything connects. Hardware funds software. Software collects data. Data trains AI. AI improves hardware. And infrastructure expands reach. A self-reinforcing machine that grows stronger every cycle. So when you put it all together, Tesla's motor is not just the most advanced in the EV industry. It is the entry point into a much larger ecosystem that connects data, AI, energy, and manufacturing into one continuous loop. But this raises two important questions. If Tesla's advantage keeps compounding at this pace, what does competition even look like 5 years from now? And, more importantly, are we still looking at a car company at all? Let me know your thoughts about this in the comments below. If you liked this video, make sure you give it a thumbs up. And if you don't want to miss what's happening in the automobile industry around the world, subscribe to the channel. We'll see you in the next video.